How long would a realistic mission to each of the planets in our solar system actually take? Not the science fiction version with warp drive, but what would actually be feasible with our current or foreseeable technology. When I talk about a realistic mission, I mean real trajectories, real propulsion systems, and real physical limitations. A realistic mission takes into account, for example, that planets are constantly moving, and that a spacecraft can therefore never simply fly straight ahead, but must follow a carefully calculated curve. It also takes into account that fuel is heavy, that every kilogram counts, and that some journeys simply take years, no matter how good our technology is. For decades, we have been sending probes through our solar system: Voyager, Cassini, New Horizons. We have rovers on Mars, a probe in orbit around Jupiter, and plans for manned Mars missions this decade. Technology is developing rapidly, from classic chemical rockets to ion thrusters to nuclear propulsion systems, which are currently under development. The bad news: the distances in the solar system are simply gigantic. And that's precisely what makes the answer to our question so fascinating and sometimes sobering. Let's begin. Before we get to the individual planets, we need to briefly discuss physics. Because space doesn't work like a highway where you can just step on the gas and drive off. Here, gravitational forces and laws that Johannes Kepler described back in the 17th century reign supreme. All planets move in elliptical orbits around the Sun, and faster the closer they are to it. A spacecraft leaving Earth is already on such a path. To reach another planet, it has to deliberately alter this path, and that requires energy. This is exactly where gravity assist comes into play. A probe flies close to a planet and uses its gravity like a slingshot, acceleration without any fuel. The most important planning tool remains the Hohmann transfer, the most energy-efficient connection between two orbits. Economical, but not fast. Another factor is the propulsion system for our mission. To this day, the standard propulsion system for space travel is the chemical rocket. Powerful at launch, but fuel-hungry. For long distances, ion thrusters come into play. They are extremely efficient and can accelerate spacecraft continuously for months, but they provide only very weak thrust. But let's start now. How long would it take us to reach our planets? First, the inner planets, beginning with Mercury. Mercury is the planet closest to the Sun, between 77 and 222 million kilometers from Earth, depending on its position. Sounds like a short trip, but the opposite is true. Precisely because Mercury orbits so close to the Sun, it is extremely difficult to reach. A direct flight would make the spacecraft far too fast. It would have to decelerate massively to avoid simply flying past it. That's why missions like Bepi Colombo use several gravity assist maneuvers at Venus and Mercury itself to reduce speed. The result? The journey takes about 5 to 7 years, significantly longer than to Venus, even though Mercury is closer to us. Venus is our nearest neighbor, only 38 to 261 million kilometers away, depending on the constellation. Under favorable conditions, it is the fastest planet to reach, only 3 to 5 months of flight time. The optimal launch window opens every 19 months. Historical missions like Venera and Magellan have already used this route multiple times. For manned missions, Venus remains problematic for other reasons. But purely in terms of travel time, it is the easiest destination in the inner solar system. Next up is perhaps the most interesting planet for us as humanity: Mars, the red planet. Mars lies between 56 and 401 million kilometers from Earth, depending on where both planets are currently positioned in their orbits. The optimal launch window opens every 26 months when Earth and Mars are in opposition. At this time, the distance is shortest and the trajectory most efficient. Virtually all previous Mars missions, from Mars Odyssey to Curiosity to Perseverance, had travel times between 6 and 9 months. The average is about 7 months. This duration results from the Hohmann transfer, the most energy-efficient route. For a manned mission, one would expect a one-way trip to take 8 to 9 months. Then comes the crucial waiting period. The astronauts must remain on the surface for approximately 500 days until the next favourable return flight window opens. The return flight itself takes another 8 to 9 months. The total mission, about 2.5 to 3 years. SpaceX and NASA are planning precisely around these timeframes for the first manned Mars missions in the 2030s. However, such a mission still faces many challenges, and the astronauts who travel to Mars will have to stay there for a variety of reasons. I've already uploaded a detailed video about this. The next planets are our ice and gas giants, starting with Jupiter. Jupiter is the first true colossus and the beginning of truly long journeys. Its distance from Earth varies between 588 and 968 million kilometers, depending on its position in its orbit. That's between 4.2 and 6.2 astronomical units. The fastest missions to Jupiter, like New Horizons, which only made a flyby on its way to Pluto, took about 13 months. But that was an express mission without brakes. Probes that were actually intended to enter orbit around Jupiter took significantly longer. Galileo took 6 years, Juno 5. The trick is gravity assist. By cleverly using Venus, Earth, or Mars for gravity assist maneuvers, the travel time can be reduced to 2 to 3 years. The currently running Europa Clipper mission will arrive in 2030, after about 6 years of travel time. For a manned mission, 2 to 3 years with gravity assist would be realistic, but even that would be an unprecedented challenge. Next up is Saturn. Saturn is even further out, between 1.2 and 1.7 billion kilometers from Earth, about 8.5 to 10.1 astronomical units. The distance is double that of Jupiter, and the travel times increase accordingly. Pioneer 11 took just under 6.5 years, the Voyager probes about 3 to 4 years, but only because they already had tremendous speed after a Jupiter flyby. The Cassini-Huygens mission, which entered Saturn's orbit in 2004, had a flight time of 6 years and 9 months, including several flybys. For a realistic crewed mission, one would expect a 3 to 4 year journey, assuming one uses Jupiter for a speed boost. A direct flight would take 6 to 8 years. Now we come to our ice giants, way out in our solar system. Let's start with Uranus. Now things are getting serious. Uranus lies approximately 2.6 to 3.15 billion kilometers away, between 18 and 20 astronomical units. Only one probe has ever visited Uranus, Voyager 2 in 1986, after a flight time of 8.5 years. For a modern Uranus orbiter mission, such as the one NASA is planning for the 2030s, a travel time of 9 to 13 years is expected, depending on how many gravity assist maneuvers can be used. A manned mission to Uranus would take 12 to 15 years for the outbound journey with current technology, and the return journey would extend the total mission to 25 to 30 years. Realistically, such a project is therefore practically impossible at present, except with future propulsion technologies. Even further out, we come to Neptune. Neptune is the ultimate challenge. 4.3 to 4.7 billion kilometers from Earth, around 29 to 31 astronomical units. Here too, Voyager 2 is the only reference point. The probe took 12 years to reach Neptune in 1989. For a hypothetical Neptune orbiter mission, one would currently expect a direct flight time of 12 to 14 years. With perfect gravity assist maneuvers at Jupiter and Saturn, this could be reduced to 9 to 10 years, but even that represents half a generation's wait. Neptune remains the most unreachable target in the solar system for the foreseeable future. To summarize, How long would a manned mission to each planet take, realistically speaking? Mercury. About 5 to 7 months for the outbound journey with gravity assist maneuvers. Paradoxically, one of the most difficult targets despite its relative proximity. Venus. Only 3 to 5 months, the fastest planet to reach. The journey isn't the problem, but the destination itself. Mars. 8 to 9 months for the outbound journey, 500 days on board, 8 to 9 months for the return journey. Total mission, 2.5 to 3 years. This is feasible, and will likely become a reality within this decade. Jupiter. 2 to 3 years with gravity assist. An enormous challenge, but theoretically possible. Saturn. 3 to 4 years with gravity assist, 6 to 8 years without. Here we are slowly leaving the realm of manned missions. Uranus. 9 to 13 years, simply too long for humans with today's technology. Neptune. 12 to 14 years, or 9 to 10 with perfect maneuvers. Those were all our planets, and the time we would theoretically need to reach them. I would find it truly fascinating if we could manage to visit and explore all the planets, but unfortunately, that will remain impossible for the foreseeable future. Nevertheless, the history of space travel shows that the impossible is only a matter of time. Perhaps one day, we will see propulsion systems that halve or quarter these travel times. Until then, the outer solar system remains the realm of robots. I hope you enjoyed the video and would appreciate your support. I hope to see you next time.